Now, the fundamental lemma, therefore, gives us a very practical way, as I already remarked. Let us see a trivial example. Okay, let f of xy be, say, xy sine x. Now, the partial derivatives would be, because y is constant, derivative with respect to x, so that would be derivative of the first term. It's the product rule, sine x plus xy times the derivative of the second term. Similarly, del f del y, now this time x is constant, so we just differentiate with respect to y. It's x sine x. Now, clearly, we have trigonometric functions and polynomials and products and sums. So both of these functions are continuous everywhere. Okay. But this says that by fundamental lemma, okay, f is differentiable everywhere. As this example shows, if we have nice functions put together, that is trigonometric, polynomials, exponentials, and so on, then at any point, okay, wherever they are defined and differentiable, they will give us continuous partial derivatives, and differentiability will be valid. Okay. Now, an example showing that the fundamental lemma is not an if and only if statement. This is instructive, therefore I will spend some time on it. An example showing that f is differentiable at p0 does not imply f sub x, f sub y are continuous. So, converse of fundamental lemma is false. Okay, the example is the following. Of course, you expect a strange example. Sine of 1 over root x squared plus y squared. If xy is not 0, 0, and 0 if xy is 0, 0. Of course, this function is continuous and differentiable, etc., except at 0, 0. And this is precisely the point we will have to investigate. Then, okay, as a first step, let us find fx at any xy. Now, this is something we are doing actually first time. This is not finding the value of f sub x at one particular point, but at all points, namely as a function. Clearly, we will have the following distinction. If p0 is 0, 0, probably it will be different but at other points, it will be different. Namely, okay, namely if xy 0 is not 0, 0, then, okay, because it's not equal to 0, 0, it's far away from 0, 0. There's a distance between them. So for all points near this point, the value of the function will be the top expression. Okay. Then, okay, for all xy near x0, y0, fxy will be then x squared plus y squared sine 1 over root x squared plus y squared. So, f sub x at x0, y0 will be directly the derivative keeping y constant. And you just routinely differentiate. That means we have a product derivative, so it is 2x, derivative of the first, times the second term, okay, plus the first term times the derivative of the second term and then derivative of the inside part, so that would be minus half 1 over x squared plus y squared to the power 3/2 times 2x. Okay. Now, we will evaluate it at the point x0, y0, so these are all x0s. Now, this says, of course, that if x0, y0 point is not 0, 0, well, this is the derivative right away. And fx at 0, 0 would be, of course, you cannot use this formula anymore, so because of the piecewise definition, we have to evaluate the limit x approaching 0, f of x0, f of 0, 0, divided by x minus 0. But this is, of course, f of 0, 0 is 0 by definition. The other one, because x is not 0, it goes to 0, okay? We keep x, instead of y, we put 0. So this is then the limit x going to 0, where y is 0, we have x squared sine 1 over root x squared divided by x. Okay, from one variable calculus by squeezing theorem, this is 0. As we recall. Okay. Now, this tells us that the derivative with respect to x will be the following. It will be this long expression, namely 2x sine 1 over root x squared plus y squared, okay, minus 1/2. Now, we can, of course, simplify things a little bit, okay? This simplification will tell us that we have just 1 over root at the bottom. That is, this would be, okay, this 3/2, so it is the square root at the bottom. So that would be 2x0 divided by square root of x0 square plus y0 square. And I think we have cosine 1 over root x0 square, x, I mean, the zeros, of course, just this, plus y squared. Okay? If xy is not 0, 0. Okay. And as we calculated, at 0, 0, the derivative with respect to x will be 0 if xy is 0, 0. So these are all values of f sub x, namely it exists everywhere. So we don't have any trouble there. Now, let xy approach 0, 0. We are checking continuity. Does this whole thing approach 0? Okay. So when xy approach 0, 0, this term, clearly this part, okay, will give us something which does not go to 0. Namely, especially when y is taken to be 0 in this limit, okay, this will give us a problem. Let me show it. Okay. Limit xy goes to 0, 0, f sub x xy does not exist because, okay, when the point approaches 0, 0, okay, as xy approaches 0, 0 on y equal to 0, okay, that means, of course, on the x-axis, we get limit x going to 0, because y is already 0, we have f sub x, x 0, and that would be x approaching 0. Okay. Now, if you look at this expression, it's 2x sine 1 over root x. That's this x squared. So this term. And we have minus 1/2 of 2x over root x squared, and finally cosine 1 over root x squared. Okay. This is just taking the limit when y is 0. But clearly, this part goes to 0 by squeezing theorem, but this part does not have a limit because, okay, this 2x over absolute x, when x approaches 0 from right or left, goes to 1 or minus 1. But cosine 1 over absolute x, when x approaches 0, just dances between minus 1 and 1, and very rapidly when x is near 0. So this goes nowhere. Now, because on a curve this limit does not exist, so limit xy approaching 0, 0, fx xy does not exist. Okay. Well, this says that f sub x at 0, 0 is not continuous. Okay, by symmetry, similarly, let me say, f sub y at 0, 0 is not continuous, but of course, they both exist. namely f sub x at 0, 0, f sub y at 0, 0 by symmetry is 0. So this is an example where the partial derivatives exist, but they are not continuous. So we cannot use the theorem, the fundamental lemma, for differentiability. However, this function is differentiable because by limit form of differentiability, we have to look at the following limit. Limit when xy goes to 0, 0 of fxy minus f0, 0, okay, minus the partial derivative times x minus 0 minus the partial derivative times y minus 0, okay, divided by square root of x squared plus y, actually x minus 0 squared plus y minus 0 squared under the root. So by the limit form, we have to check that this limit is 0. Is it 0? Well, this limit is nothing but fxy, which was simply x squared plus y squared times sine 1 over root x squared plus y squared divided by square root of x squared plus y squared. Okay. Obviously, if you divide, you end up with limit xy going to 0, 0 of square root of x squared plus y squared times sine 1 over root x squared plus y squared. Now, even though it is a two-variable limit, actually it's one variable because you have just this form, nothing else. When xy goes to 0, 0, you have u sine 1 over u. Well, you can look at it as a one-variable limit, or directly you can use squeezing theorem. So this says that f is differentiable at 0, 0. So this f is differentiable at 0, 0, has partial derivatives therefore, but the partial derivatives are not continuous. So the converse of the theorem is not correct. Well, it's obvious that this theorem is extremely useful because you just calculate the partial derivatives and see if they are continuous. Now, this is pretty easy with elementary nice functions. But of course, with strange functions like this, you need to work a little bit more. Okay. Let us make use of the meaningful linear approximations. So, examples on linear approximations. Well, this will mean tangent plane approximation once we define it. us start with, actually, I will not have too many examples here. Say we want to find the square root of 1.02 times 1.99 squared. Or rather, should I say cubed? That's actually, it becomes trivial this way. So, fine. Okay, find this by using linear approximation. The idea is that, of course, you can take this out, so this is not a perfect example, but nevertheless, we want to use a two-variable function to describe this. Namely, okay, we define a function here, and we want to use linear approximation for this function at the point, of course, 1 and 2. Okay. Clearly, at the point 1, 2, okay, we have just very small deltas asked. And therefore, okay, the linear approximation will be meaningful because this function is differentiable. We can calculate the derivatives. So let us do that. F sub x at xy, okay, would be the derivative with respect to x. Namely, it will be 1 over 2 root x times the constant. And f sub y at xy, okay, this would be, well, root x times the derivative of absolute y. Okay. So that would be 1 or minus 1. Well, it will be 1, okay, because our y is 2. So, with this data, we can now calculate this root. It's approximately f of 1, 2 plus, okay, the derivative with respect to x at this point, namely f sub x at 1, 2, times x minus x0, which is 1.02 minus 1, plus f sub y at 1, 2, times the point 2, okay, the x point, 1.99, okay, minus 2. So this was the differential approximation, linear approximation, or tangent line, tangent plane approximation. Now let us put what we have here. F1, 2 would be square root of 4. F sub x at 1/2, 1 and 2. Okay, this is 1 and this is 2. So it would be just 1. Our delta x would be this one. F sub y at 1, 2 would be 1 again, times minus 0.01. Now, so our approximation happens to be 1.9, sorry, 2, that's 2.01. Well, we are not at this point in a position to estimate the error, so let me just give you the beginning of the decimal expansion directly. Actually, this value, the square root, 1.02, 1.99 squared, happens to be 2.009801, and so on. This being the exact value. Okay. Well, a second example which is more or less on the same lines, but numerically better one. So the same question for the exponential of 1 over 100 times cube root of 7.99. Okay. Now the example suggests that we should consider the function fxy, which is e to the x, okay, cube root of y. So f sub x at an arbitrary point would be the derivative. So that would be cube root of y times exponential of x times y to the 1/3. The derivative with respect to y, okay, would be x times the exponential times the derivative of the cube root, so that would be 1/3, okay, y to the power minus 2/3. Okay. Well, the point certainly would be 0, 8. Now, both are continuous at this point, and so we can use the fundamental lever, that is, this is a differentiable function, and so the linear approximation is meaningful. That means the error part will go to 0. Okay. Even though we don't have a control right away. So, it says that this value, the exponential of this term is approximately f of 0.8 plus the derivative at 0.8 times x minus 0, because the first value is 0, plus f sub y at 0.8 times 8 is the x0 here, so it is 799 minus 8. Now calculations shows that f sub x at the point 0, 8, okay, is e squared, and you have 2 here. Sorry, x is 0, so this is 1. You just have 2. Cube root of 8. And f sub y is, because x is 0, it is 0 directly. So this says that the number we want is approximately, well, this of course is 2, again, if you directly put it in place, okay, sorry, if you put 0, 8, that becomes, 1. So it is 1 plus 2 over 100, and that's all. That is, it is 1.02. Just, no, I don't have any more calculations in this. Okay. Now, a word about generalizing these things to even higher dimensions. Well, the differential definition can be extended to functions of 3 variables, and even more to n dimensions directly. And all the consequences, that is continuity, that is the linear approximation, or the chain rule, all of them will be valid. Now, because of its importance, we will have some direct applications of the total derivative formula, that is the chain rule. So, now we will consider the chain rule in more detail. Okay, let us recall the total derivative formula. Namely, it says that the derivative of f of x of t, y of t, okay, would be f sub x at the same point. I will not write that. In short, x prime t plus f sub y, y prime t. If, of course, all functions here, f a function of 2 variables, x and y functions of 1 variable, have derivatives, and f has a differential. So, okay, if, of course, f, x, and y are all differentiable. Okay, so this being the basic formula, okay, that we derive from differentiability, okay, let us consider 2 points about these things. Well, firstly, what about the partial derivative form and the d form for a derivative? Namely here, let f be a function of 2 variables, then okay, d by dx f and del by del x f are not the same. Okay. What's the difference? The difference is the following. Well, yes, f is a function of 2 variables. Fine. Okay. But this says that there's only 1 variable. And we differentiate directly. Okay. How is it possible that f is a function of 2 variables, but we only have 1 variable, x? What happens to y? Well, y is a function of x. So this means, okay, y is a function of x, So we talk about the usual derivative for f of x g of x. Of course, in here, you have only one variable, so you differentiate. And by the total derivative formula, this means that we have del f del x. I don't want to use it here. Simply, let me say f1. Okay. That is the derivative with respect to the first variable, times derivative of x with respect to x, plus f2 derivative of g of x. So, this formula says that x of t is t, y of t is g of t. And then, but t is equal to x. So we get this formula. So it is f1 plus f2 times g prime x. Whereas this means that y is constant. And you differentiate directly. So the notations do not mean the same thing. We should be careful about that. Okay. A second remark is the following. Now, suppose f is a function of two variables. Fine. And x is a function of two variables, and y is a function of two variables. Now, what does the total derivative formula tell us? Well, obviously, if we consider f of x of st and y of st, this will be a function of s and t at the end. So it's a function of two variables. So I can show this as a function of two variables. Okay. And here, of course, I cannot talk about just the derivative of z as we did in the total derivative formula, but I can talk about partial derivatives. So, I can talk about del z, del s. Because there are two variables, one of them is constant. So this means t is constant. The only variable is s, and we differentiate. Well, if s is the only variable and t is constant, this fits into the standard formulation of total derivative formula. That is, x is a function of s only, because t is constant, and y is a function of s only, so it is constant. T is constant. And therefore it means the derivative of f with respect to the first variable, without this substitution, you can call this u if you want, and this v, so this is fu actually, times the derivative of xst, but t is constant. Well, it's the definition of partial derivative. Because t is constant and you differentiate this with respect to s. Similarly, this says we have f2, which would be in our new formulation, f sub v times del y by del s. So this is a slightly extended form of the total derivative formula, which will be extremely useful in our computations. Okay. Now, let us see some examples. Well, my first example is a standard one, which is a direct application. Say zdfxy, which is xy squared plus y sine x. And x is t squared, y is cosine t. Okay. We want to calculate the derivative of z. So z, if you look at the right-hand side and replace these values, okay, you obtain that z can be regarded as a function of two variables, namely z of one variable. It is f of, okay, t squared and cosine t. So we can talk about the derivative of z with respect to, just the derivative of z. Okay. Well, a word, this clearly is a differentiable function by fundamental lemma. The derivatives are continuous, easily seen. So this would be f sub the first variable, which is x in this formula, times the derivative of t squared, f sub the second variable, the derivative of cosine t. Now, f1, that's derivative with respect to x, would be y squared plus y cosine x, times derivative here would be 2t, and f2, that is derivative with respect to y, would be 2xy plus sine x, times derivative of y, which would be minus sine t. Okay. Of course, to be precise, you should put the values of x and y in terms of t squared and cosine t, respectively. Okay. So, if, for instance, we want to calculate this partial derivative, so, for example, if we want to calculate dz by dt when t is 0, say, what happens? Well, in this case, x of 0 would be 0, y of 0 would be 1. So we don't have to substitute back to t. Directly we can put the values. Well, it means that according to our computation, that this would be, okay, well, y is 1, x is 0. So if y is 1 and x is 0, this becomes 2 times 2 times 0. And here x is 0, so we get 0 directly. So the whole thing becomes 0 at this point. So we don't have to substitute back to t's, but we have to find x and y. Okay. Now clearly, as in the case of one variable, we can use the chain rule with not only one chain, but more than one chain. Okay. This means, okay, as a second example, say we have f of xy, x to the y, and x is a function of u and v, so it is u tangent v, and y is a function of u and v, it is v sine u. Okay. But u is a function of t, say t squared, and v is a function of t, its logarithm. Okay. Now, of course, t is not 0 or a negative number, otherwise logarithm would not be well defined, etc., etc. So we assume everything is in order. That is, we don't evaluate these functions at some point where they are not differentiable. So I will not emphasize that fact again. So the question is, now if you put everything in place, Okay? That is, replace xy with the uv values, replace uv with t values. I can talk about the derivative of the whole thing, okay, where t is the only variable. So, d by dt of f, okay, normally I should have written something like this. I will not do it in detail. Okay, u is a function of t, and v is a function of t, and y is a function of ut and vt. Okay. Now, everything is in terms of t, and so we can calculate this derivative. Now, let us go step by step. First of all, okay, we have t as the variable. That's what we want. So, we should have the following. We have, first of all, f of the first derivative with respect to the first variable, and this is the first variable. So I can call it f sub x if you want. Times the derivative of x with respect to t. Okay. Well, this is a little bit, of course, problematic because t is not a variable of x directly. X is a function of u and v, which are in turn functions of t. So there's a chain here as well. In other words, this x is x of ut vt plus f2, which happens to be f sub y here, times the derivative of y, u of t, v of t. Well, here some terms can be directly calculated. For example, f sub x. Well, this means that y is constant in the original formula. So it is like x to the power 3 or so. So it is y times x to the y minus 1, because y is constant. Similarly here, this time x is constant. If x is constant, it's an exponential function. X to the power y, and y is the variable. So it is itself times logarithm x. For the other ones, we need to use the chain rule once again. So let us consider now the derivative of x of u of t and v of t. Okay. Now here, x is a function of two variables, u and v, and each of them is a function of t. Well, this is a standard total derivative problem. So this is the derivative of x with respect to the first variable times u prime t, x2 with respect to the second variable times v prime t. Now, when we look at the definition of x, the first variable is u. So the derivative of x with respect to the first variable would be x sub u, where v is constant. It's a partial derivative. So when we look at the expression, it's u times tangent v, so it's just tangent v. Similarly, okay, this means u is constant. So because x was u tangent v, the derivative becomes u derivative of tangent v, so secant square of v. Okay. So this takes care of all derivatives in question. Now we have another term, y of u of t and v of t. Similar to this, it is y sub u, u prime, plus y sub v, v prime. That's total derivative formula directly. Now, y sub u, because y is v sine u, this would be v cosine u. V is a constant. Y sub v, on the other hand, because y is v sine u and u is a constant, it's just sine u. The others are the same, and so this finishes the calculation of this derivative. You have to put these things back in place to get the result. Okay. A note, the tree formulation. This does exactly the same thing, but sometimes it seems easier to students, so I want to introduce that. This means the dependence of variables. You write it as a tree. That's to say, we start with f at the top. F is a function of x and y. Well, that is what we have directly. It's x to the y, actually. And then x and y are functions of u and v. So we have u and v. And finally, u and v are functions of t. Now, how do we use this graph? Well, in calculating the derivative of f with respect to t, we have to go through all possible branches. In short, derivative of f is derivative of f with respect to x, so it's f sub x, times x sub u. Okay, let me write that in a minute. So go through, okay, all possible branches. Okay, that lead to t. Okay, that means derivative of f with respect to t would be, okay, let us start with the first branch here. It's f sub x times x sub u times u prime t. Okay, that's the first branch. The second branch would be, again, f sub x, but then x sub v this time, and then v prime t. This is the second branch. Plus, now f sub y, y sub u, times u prime t, and finally, f sub y, okay, and then y sub v, and v prime t. Okay. Now when you calculate everything here, the point is, of course, because of the tree, all of these derivatives are without chain. Namely, x is a function of u and v. That's all. And you keep v constant, take the derivative. Similarly for the others. Okay. So this is simpler perhaps, but there's a bad thing about it. When we calculate second order derivatives, this fails. So this approach, or let me say this method, works only for first order derivatives. Not for higher orders. Okay. And as you can expect, We will consider such examples in a minute.